Okay, I just realized that this part is not visible, so I'm going to take it up. Should be fine now.
Actually, that's when you've made it. That's better. Yeah, that's okay.
So this is -1 over L raised to -b to evaluate this. So there are so many rules you could use here. There is this rule we gave that if you have a number p raised to -n divided by q raised to -m, then you could just flip these fractions, but then change the sign of the exponents. Change the sign of the exponent. You don't change the sign of the base. So this, you should get q to the m divided by p to the n. And we prove this. In this case, take the first -1. You remember, -1 divided by a is the same as -1 divided by a, which is the same as 1 divided by -a. All these are the same. So in this case, I'm going to flip these guys and then change the sign. So I will have a divided by -1 raised to b. I've changed the sign of b. The sign of the base does not change. Okay, so now remember that any number divided by -1 is the additive inverse of that number. So this should simply be negative of a raised to b. Remember, always remember to put the bracket, because if you write -a raised to b, this is not always the same as -a raised to b. These two numbers are not the same. So in the first instance, you raise the number to b and then take the negative of that. But in the second one, even the negative is raised to b. So the second one, when you write -a to the b, this is the same as taking -1 raised to b times a raised to b.
I can't see what you've written. The screen, I can't see in, like, the only part I can see until -b to the power of b, -a to the power of b is not equal to.
Okay. How about now? Maybe I'll use this other part of the board. I wanted to emphasize that when you put a, this is not the same as negative of a raised to b. And I explained the difference. The difference is that in the first instance, you raise this base to b and then take the negative of that. In the second instance, it is the whole thing that is inside the bracket that is raised to b. So when you write negative of a raised to b, this means you're taking negative of a, you do that b times. Okay, you do that b times. But the second one, negative of a raised to b, this means you're taking negative a times negative a times negative a times negative a, and you do that 3 times. So these are two different numbers. I noticed that some of you are writing this, which is not correct. Any question on this? Any question on this?
Yeah, so if we wrote our answers like -a, b is wrong.
Yeah, that's wrong. Because
Oh,
it's different. The second one, you can also put this as -1 raised to b multiplied by a raised to b. Because it's just like, -1 is present in each and every term, and this term negative a is written b times. So it's the same as pulling out -1 b times and then a by itself b times. Any other question? Okay, what was the next problem?
simplify using negative exponent.
Sorry?
Eliminating the negative exponents.
Eliminate the negative exponents, and what did you have?
Y to the power of -8.
Negative.
Z.
S, not 8.
S, not 8.
S.
Oh, okay.
I don't know why most of you use 8. Then
Z over PZ raised to negative T Y. Yeah.
raised to minus x, I think.
Negative x.
Yeah, raised to negative X.
Good. So there are only 2 rules you are supposed to apply here, and that's why this question was 2 marks. If you got the right, there are only 2 rules you are supposed to apply. The first rule is the flipping. You flip and then change the signs. This rule, which we've written so many times, a to the minus n divided by b to the minus m is the same as b to the m divided by a to the n. I just take b upstairs and change the sign of the exponent to positive, and take a downstairs, change the sign from minus n to n. Now in this case, I have y to the minus s and z to the minus t. Those are the only terms I need to flip, because my goal is to eliminate all the negative exponents. So first, we have z divided by, so down here we will have p times y. Now z to the minus t, take it upstairs and change the sign to t. So here times z raised to t. You have a y to the minus s up here, take it downstairs, change the sign to positive. So times y to the s. And then there is this to the negative x. So in my first procedure, of my first step, I've ensured that there's no negative exponent inside this bracket by flipping the terms that have the negative exponents. If it is up, I take it down. If it is down, I take it up. Okay. Then now we need to change the sign of this exponent up. There is this rule that a to the minus n. Yes.
Sure, could you repeat how you got in, how you did the first step, because it's not clear.
It's not clear. Do you remember this rule?
Mm-hmm.
We proved this rule that if you have negative exponents and you want to eliminate them, just flip the fractions. Take the denominator to the numerator and change the sign from negative to positive, the sign of the exponent. So in this case, the exponent is negative m. Take it up, the exponent becomes positive. And then the one that has negative n, take it down, the exponent becomes positive. So what I've done here, you notice that we have y to the negative s and z to the negative t in the numerator and in the denominator. So the first step is to take this y to the minus s down and change the sign to s. So that's what we have. That's why we have y to the s down here. Py, we just maintain them because their signs are positive. And then z to the minus t, take it up, change the sign to positive. So zt times z that we had here.
But those letters are like 1 unit. How can you just be taking one up and the other one down?
No, there's a multiplication. It's a multiplication.
Yeah, there's multiplication. So why are you just taking the z up?
There's no problem. Remember, I can write this as y to the minus s divided by z to the minus t times z divided by py. I can write whatever it is inside this bracket like this. Then this way, I can change what we have, what I've shaded in blue. I can do the flipping, and I have z to the t divided by y to the s multiplied by z divided by py, which is what we have inside here. Did that make it better?
No,
No.
I'm still not getting what you're doing.
Me too, I'm still not
Sorry?
understanding.
Okay, so how do we do this? What's the problem? Is it that you're not convinced of this rule? Should I prove this? Because we did this in class before. Okay, let me give it a different approach. Let me give it a different approach. When you write y to the minus sz, this simply means y to the minus s times z. That's the meaning of this expression, y to the minus sz. Y to the minus s times z. Similarly, p times z to the minus t, y, this means p multiplied by z to the minus t multiplied by y. So, suppose you had numbers. For example, you can write 30 as 2 times 5 times 3. And suppose you also have maybe a 15 written as 3 times 5. So that 30 divided by 15 is the same as 2 times 5 times 3 divided by 3 times 5. Then now I just divide the like terms and remain with what is not common. So similarly, in this case, I'm only interested in the terms that contain the negative exponents. My goal is to eliminate the negative exponents and leave the ones which have positive exponents the way they are. So that's why I'm not caring about z, p, and y. I only take the terms which have negative exponents. So the rule that you're using is that if you're changing, so if you have a fraction, a to the minus n divided by maybe p to the minus s, just take what is in the denominator to the numerator and change the exponent to positive. So this should be p raised to s divided by what is in the numerator is a to the negative n. So we put a down and change the sign to positive. So the first step, write this y to the minus sz divided by p z to the minus ty as y to the minus s divided by z to the minus t multiplied by z divided by py. Then this is the fraction of interest. It is the one that contains negative exponents. This guy is fine. All the terms have positive exponents. And when you apply this law, if I flip the fractions, then change the sign of the exponents, I will do away with the negative exponents. So in this case, the fraction is y to the minus s divided by z to the minus t. So I just take what is in the denominator upstairs and change the sign of the exponent from minus t to positive t. And take what is upstairs down and change the sign from minus s to s. Does that make it better now?
Yes.
Hello?
Yes,
Is that better now?
yes, thank you.
No, if it's not fine, just be honest. Don't say yes to.
I have a question.
Yes, go ahead.
Where did the x go? The negative x?
The negative x. Yeah, the negative x is still there. We still have this raised to the minus x. So that is the next goal. The first goal is to change this, make sure what is inside the bracket, all the negative exponents have been eliminated. And the way we have eliminated the negative exponents is that if there is a term which has a negative exponent, if it's the denominator, take it the numerator and change the sign of the exponent. If it is in the numerator, take it down and then change the sign of the exponent. That is what we have done in the first step. Now the next step is to change the sign of this outside exponent, this minus x. How do we do that? And in this case, the rule that you need to apply is this definition. If you have a raised to minus n, this is the same as 1 divided by a raised to n, which simply tells you that if a number is raised to a negative exponent, it is the same as having this as a fraction, but now in the denominator, you change the sign of this exponent. So for example, You can even confirm this, that 2 to the minus 3 the same as 1 divided by 2 cubed, which is 1 over 8. You can find this in your calculator and get this answer. So in this case, what you do here, first of all, there's a rule you can apply. This is z to the t times z. There's a y to the s times p, and then times y. You can also add this. So you have this rule that an times an, add the exponents. So if you're multiplying two exponents with the same base, just add the exponents and raise the base to the sum of the exponents. So in this case, you have a z raised to a t. Z itself the same as z raised to 1. This is y to s, y itself the same as y raised to 1. So what we have there can be written as, we can write this in the numerator. In the numerator, we can have z raised to t plus 1 divided by p y raised to s plus 1. All these raised to minus x. So here I've applied this rule that if you're multiplying two bases raised to the same exponent, take the base, it's the same as taking the base and raising it to the sum of the exponent.
Excuse me.
Yes.
We can, I can see there is a bit of light reflecting on the left-hand side of the board.
This side?
Yes.
Okay, let me move the board. How about
That's
now?
perfect. Thank you. Yeah, that's perfect. Thank you.
So now the last thing that we need to do is to do away with this negative sign. And we have said the only way to do that is to write this as a fraction and then change the sign of this guy. So what I'm going to do is to flip what we have here, and then this will become positive. So then what we have in the denominator goes up, divided by what we have in the numerator, goes to the denominator, and then this guy becomes positive. Okay. So I've used this rule where now A is everything that is inside this bracket. And then you can leave it at this stage, or you can go ahead and apply the raising of power to a power, and you're supposed to get p to the x times y to the s plus 1 multiplied by x divided by z raised to the t plus 1 times x. So either of this, I was avoiding either of this because here you've succeeded in eliminating all the negative exponents of this. The only two rules you needed to apply was taking the denominator to change the sign of the exponent of a base, and then flipping the terms. So what is the numerator goes to the denominator, what is the denominator goes to the numerator, and the signs change from negative to positive. This is all that you were expected to do in that question.
Excuse me.
Yes, go ahead.
Was it correct to do the p to the power of x, y to the power of sx plus x over all that over z to the power of x plus t?
Yeah, it's okay. It's okay.
Okay.
It's okay to do this as p to the x, y sx plus x divided
and we can see there. Sorry.
Let me take it up. It's okay now. This is what you're referring to: p to the x, y to the sx plus x divided by z to the tx plus x. Is that what you're referring to?
Yes.
Yeah, that's okay.
Okay.
Okay. Next question.
Before we proceed,
yes.
Me, I honestly saw that S as 8. I don't know if I have a problem with my eyes.
I saw it as 8.
I got the same answer, but now my Y had, instead of the power S, had the power 8.
So you ended up with to the power 9.
Yeah, I ended up with PY to the power 9.
Okay, just check your Blackboard.
Okay.
Check and see how. I can't remember what I did, but I didn't deny you all the marks. Huh? Those who use S as 8.
Okay.
I didn't deny you all the marks, but you can check.
Okay.
Excuse me, sir.
Sorry.
I have a question.
Yes.
Okay.
Could you give a makeup assignment for this?
For this assignment too.
Yes.
For everyone.
For those who feel like they didn't do as well, and yeah, for those who didn't do the assignment as well.
Well, I can give a makeup assignment, but it's not going to be as simple as the first one.
Okay, because there's some things I just did not
Yeah,
understand.
Okay, we can discuss that. We can discuss that
Okay.
later.
Excuse me, sir. I have a question before we proceed to the next question.
Yes.
If I'm not wrong, there's a time when we were learning about negative exponents, we said that a to the power of negative n can also be written as 1 over a to the power of negative n. So what I did is, instead of changing them, or like put now pys plus 1 as the numerator, I just put this whole thing as another fraction. Like now I wrote 1 over z plus t, 1 over z to the power of t plus 1. So I'm just wondering if that's still okay.
You're saying that we write 1 over z plus 1 divided by p y to the s plus 1 raised to x. Is that what you're referring to?
Yes.
Yeah, that's okay.
Yes, I am.
That's okay.
Okay.
The same rule here.
Okay.
That's still okay. More questions? What was the next problem?
Combine the following radicals.
Combine the following radicals. It was root 50 plus root 8.
8. Yeah.
Supposed to combine these two. Okay. So remember, you can write 50 as 2 times 25. Okay. And you can write 8 as 4 times 2. Maybe you're asking why. So how did I choose to write 50 as 2 times 25 and not 10 times 5? I'm looking for factors of 50 and 8 which are perfect squares, which can give me square roots which are rational. So 50, the only factor it has which is a perfect square is 25. 8, the only factor it has which is a perfect square is 4. That's why I chose to write 50 as 2 times 25, 8 as 4 times 2. Then now at this stage, you remember the rule that the square root of a to the a times b is the same as square root of a times square root of b. That the square root of a product is simply a product of the roots. So you can write this as the square root of 2 times the square root of 25 plus the square root of 4 times the square root of 2 by applying this law. Square root of 25, everyone knows that. That's going to be 5. So this becomes 5 times square root of 2 plus square root of 4, everyone knows that's 2. So plus 2 times square root of 2. Now at this stage, remember these are real numbers. And there is this distributive law that A multiplied by B plus C is the same as AB plus AC. So you're supposed to use this distributive law to combine this. So the way it is in this second form. Now you're supposed to take it back to the first form. So 5 root 2 plus 2 root 2. If you factor out root 2, you will have 5 plus 2 multiplied by root 2, which gives you 7 root 2. That's the final radicals. There are some people who are getting 14. I really tried to understand how they're getting from 14 from this, but I didn't. Maybe they can explain to me. I didn't quite understand how they were getting 14 from this.
Maybe they thought the plus was times, so when you times root 2 times root 2, you get 2. And they added directly 5 plus 2, which was 7. So 7 times 2 was 14.
Well, if this was a multiplication, then you should get 20, not 14.
No, I mean, they only saw the part for root 2 times root 2.
Okay. I don't know.
Excuse me, sir, I have a question.
Go ahead.
In such type of a question, do we always have to have the same answer, or does it vary?
What do you mean by do you always have the same answer?
Like, is everyone supposed to have like 7 root 2 as the answer, or can you have another answer as the answer, but like having followed the right steps?
Give me an example.
Like say in the case of getting the square root of 25 and 4, you would like instead just add like 25 plus 4, and then like the answer will be 29 root 2 or something, instead of like going the extra way of finding the square roots.
You're saying the answer should be 29 root 2.
A possible answer.
That's not a possible answer, because you can even confirm from your calculator. Just press in your calculator, what is root 50 plus root 8, and then plus 7 times root 2. Should give you the same answer. When you're asked to combine a radical, you're simply asked to write another expression that has the same meaning, that will give you the same number that is represented here. There is no law that combines this. This can never be equal to 29 times square root. This is something you can prove with your calculator. These two numbers can never be the same.
Okay.
Yes. What's the next question? Let's try to be fast.
Evaluate I to the power of 2022.
I to the power of 2022. So the only definition you need here is that I squared is -1. And I must say I really enjoyed marking this question, because you guys were so creative. There are so many. In fact, I had more than 10 different ways of you guys doing this problem and getting the same answer. That was very impressive. Okay. So I'll just show the method I think is simplest. So you can write 2022, you can write this as 2 times 10, 11. Just do a factorization. So that means I can write I to the 2022 as I raised to 2 times 10, 11. I've just factored this guy. Then you remember there's a law which tells you that a raised to the n is the same as a raised to the m n. So in this case, take a as I, take this as m, and take this guy as n. So you can write I raised to the 2022 as I raised to the 2 times 10, 11. You can write this as I squared, all of it raised to 10, 11. By applying this law. We all know that I squared is -1. That's the definition. So what is this? I squared is -1. So this means you can write this as -1 raised to 10, 11. 10, 11 is an odd number. So -1 raised to any odd number will simply be -1. And that's
marks was this question?
Sorry?
How many marks was this question?
Yeah, this was just 1 mark.
Okay, and then also maybe just a request for future assignment. If you can kind of assign marks to each question that we know like how much is required of us.
Oh, okay. I'll do that.
Yeah.
I'll do that. Any more questions on this?
No.
No question. What's the next problem?
Theta plus beta I over A minus BI.
Yeah, here I saw some very funny. I had some very funny responses. Some people went and changed this alpha to A, and then some people changed this. Some people instead of doing this, they did A plus BI. But it's okay, yeah?
Maybe it's because beta sometimes looks like an A. So, because even me, I struggled a bit with the knowing that it's beta.
It's an alpha.
Alpha. Well, alpha is
alpha. Yes.
Alpha is simply A in the Greek alphabet. It's the first letter of the Greek alphabet. So, and then beta. Is the second alphabet of the Greek alphabet. So actually, capital A in the Greek is simply the normal A that we have. Capital beta is simply the B that we have. But that's not necessary. So you're supposed to divide these two complex numbers. How do you divide complex numbers? Take the complex conjugate of the denominator. In this case, the complex conjugate of the denominator, simply change the sign of the imaginary part. It's A plus BI. Then use this A plus BI to multiply both the numerator and the denominator. So you should have alpha plus beta I divided by A minus BI. All these I need to multiply by A plus BI. And then the same to the numerator, A plus BI. Okay. So I was adding the first mark. This question was 2 marks. First mark I was adding for correct use of the correct conjugate, complex conjugate. So when you get the correct complex conjugate and use it to multiply this, that was 1 mark, and then the other mark was for the correct answer. But if you just give me the correct answer like that, don't expect to get full marks, because I'm not sure how you arrived there. So here we will have alpha multiplied by A plus BI plus beta I multiplied by A plus BI, all that divided by A squared plus B squared. You know that a complex number multiplied by its conjugate is simply the square of the absolute value. So this straight away is A squared plus B squared. And then, so here we have alpha A plus alpha BI plus A beta I, then minus B times beta. Minus because I times I is negative, so B times beta. Divide this by A squared plus B squared. And we finally have alpha A minus B beta. All this divided by A squared plus B squared plus alpha B plus A beta. All this divided by A squared plus B squared times I.
Do you mind moving the board a bit to the right?
To the right. So let's see.
Yeah, it's only the I we can't see. No, the other side now.
The other side.
Yeah.
Oh,
is that better?
Yes, perfect.
This is better.
Cool. Questions? Division of complex numbers is very simple. Identify the correct complex conjugate, use it to multiply numerator and denominator. The only thing you need to remember is that I squared is -1. Although here some of you are leaving I squared as part of the answer.
What did you write?
I have a question.
What did
Okay,
I
go
write?
ahead.
After A,
Here. Where? Which part are you referring to? Can someone talk? What's not happening? I don't seem to get anywhere.
Excuse me.
Yes, go ahead.
And why is it becoming a negative? Alpha beta I minus b beta here on above. Yeah.
Yeah, that's a nice question. So the last term here is beta I multiplied by bi, right? Which is the same as b times beta multiplied by I squared. But by definition, I squared is -1. So automatically this becomes minus b times beta, which is what we have here. And then now when I separate real parts, so the real parts, the parts which do not have I, so alpha A and minus beta B. That's why I have alpha A minus beta B here. And the rest
Excuse
of
me?
that part.
Excuse me, sir?
Yes.
Why do you have A better than beta A? Is that a problem?
No, there's no problem.
Okay.
There's no problem because we know multiplication is commutative. So when you write AB or BA, this is the same. Multiplication is commutative.
Okay. Let me give my answer. I have is A beta minus B plus A. I don't have beta B here. I have AB.
Why? Oh, I think you are those guys who put this as A. Maybe
Yeah.
maybe use this as A.
Yeah.
Yeah. And this is what I meant by communication. If there's something which is not clear, write to me an email immediately. Don't wait. Okay. So if there's something you're not sure about, don't just discuss among yourselves. You have to let me know that there's a problem with some question or words. If the writing is not clear, write to me an email immediately, or even call me. Okay. Next question. What was the next question?
Z cubed minus 1 is equal
to 0.
The cube roots of this guy, and then represented this in the Cartesian plane or in the Gantt diagram. So you remember 1 is the same as exponential 0i. Okay. The first step is to write 1.
You can see on the board.
We can't see there. It's too high.
It's too high.
Yes. Yeah.
Okay.
So the number 1 can be written as exponential 0i. You can convert 1 from this. Remember 1 is the same as 1 plus 0i. This is in rectangular representation. So this in exponential form is simply exponent 0i. Okay. Or if you like, you can write 1 times exponent 0i, where 1 is the absolute value of this guy. And 0 is the angle of the argument, because in your Gantt diagram, the number 1 lies on the horizontal axis on the positive side. So all the positive real numbers have an argument of 0 because they're lying on the positive real axis. Remember, all the measurements are taken from the positive real axis. So any number that lies on this positive real axis has an argument of 0. Now we need to apply De Moivre's theorem, which tells us that z raised to 1 over n is simply r raised to 1 over n exponent of theta plus 2k pi divided by n I, and k runs from 0, 1 all the way to n minus 1, so that you have n distinct roots. In this case, I expected 3 distinct roots. R is 1. So straight away, z is going to be exponent. So our angle in this case is 0. So we'll have 0 plus 2k pi divided by 3 I, 3 because we're looking for cube roots. So this is the general form you're looking for the nth roots. And for this case, our k will run from 0, 1 up to 2, where 2 is n minus 1. N is 3, so 3 minus 1 gives you 2. Now consider all the 3 cases and get the 3 roots. So the first case is when k is 0. When k is 0, then the first root will give you exponent of 0i divided by 3, which is simply 1. So
I can't see
Go below that point or raise the board just a bit. No, you've gone too far.
Too far?
Yeah, we can't see the top now. There.
Yes.
Oh no, you've gone too far again. Yes.
Okay, now?
Yeah, but don't go below that sentence now.
Maybe I can now write this side.
Yeah.
You can write smaller here.
So the first root, when k is 0, root exponent 0 is 1. Then the second root is when k is 1. When k is 1, so put here k is 1, it will be 0 plus 2 times pi, which is 2 pi. So 2 pi divided by 3. So that should be the second root. It's exponent 2 pi divided by 3. Then the third root is when k is 2. It's exponent. So you put here k is 2. 2 times 2 pi. So that's 4 pi. So that's going to be exponent 4 pi I divided by 3. If you like, you can leave your answer in that form, or you can go ahead and convert them to rectangular coordinates, but I'll be fine with this. It's okay. And then you are supposed to locate this, the Cartesian diagram. It's going to be a unit circle. The first root is going to be there. The second root is going to be after 2 pi divided by 3. The third root is going to be after 4 pi divided by 3. Z2, Z3. This is all you are expected to do in that question. So these are the three roots of 1 represented in the complex plane. So if you take this number, 1 cubed is 1. If you take this number cubed, you get 1. If you take this third number cubed, you should also get 1. Next question, unless there's a question on this. Next question.
I did mine differently.
Yes. There was a, I think I remember. So some people wrote z cubed minus 1 as z minus 1 times z squared plus z plus 1 is equal to 0. This is what you did?
No, I didn't. That's not what I did.
Yeah, but this was also another approach, which was also giving a correct answer, because here you'll apply the quadratic formula to get these two other roots. This was also a nice method, which I saw some of you use. It's okay.
So what if you introduced roots instead?
If you did what?
Was it possible to have reached an answer if one introduced roots?
I don't get the last statement. The last statement.
If we introduced root, like we now did now the cube root of z cube, I don't know.
Like writing cube root of 1.
Well, yes, and also like cube root, like just generally introducing roots.
Oh, so now what exactly do you mean?
Like there was, what I did was I wrote.
Are you talking of now taking the cube root on both sides so that z is the
exactly
root of 1? Yeah, that gives you only one root, but remember 1 has 3 cube roots.
Excuse me, sir.
Yes.
Could you please show me how you represent Z1, Z2, and Z3 on the pie chart on this unit circle?
That's very good. So I just use the angle. So the first is 0. The angle is 0. So I just put it on the positive plane. This is the number 1. The second root, the angle is 2 pi over 3, which is simply 120 degrees. So I just measured 120 degrees, which is 2 pi over 3. Then I repeat it up there. Then the third one is when the angle is 240 degrees. So I measure from here 240 degrees and I locate it on this circle. I've used a unit circle because the absolute value of this guy is 1. So the radius of my circle is going to be 1.
Well, thank you.
Okay, what's the last question?
It says complete the square squared plus x.
Complete the square. So when you have x squared plus x, complete the square. In general, when you're given x squared plus bx plus c, to complete the square, simply add b divided by 2a squared. This is general. So in this case, a is 1, b is 1. A coefficient of x squared, b coefficient of x. We need to add b divided by 2a squared. So b is 1, a is also 1. So this is a half square, which is giving you a quarter. So you're supposed to have x squared plus x plus a quarter, which you can also write as x plus a half squared. Now it's a complete square because you can find the square root of this. It's actually a perfect square. So if you have, suppose now you are given something like x plus a half squared is maybe 7, then to compute the roots, just find the square roots on both sides, because this on this other side we have a perfect square. The idea of completing a square is to make either the right side or the right side a perfect square. And in general, always add b divided by 2a squared, where b is coefficient of x or the linear term, a is the coefficient of the quadratic term or x squared. So that was just 1 mark. Any question on this?
Yes. If
Go
I'm
ahead.
not mistaken, in the notes it's written that you're supposed to add, like now you see how you say we're supposed to add to the equation over 2a squared. In the note it says that we have, so I'm just asking, like a half squared. So I'm just asking if there's really a difference between what we've done and adding a half.
And adding what?
A half squared.
Yeah, a half squared is a quarter.
All right, okay, sorry.
Yeah, so this is x squared plus x plus a quarter, which is the same as x plus, it's a half, a quarter is the same as a half squared.
So if you leave it as x squared plus x plus 1 over 4 is right?
Yeah, that's right. It's a complete square. Because I can write this as x plus a half squared. If you expand x plus a half squared, this is the same as x squared plus x plus a quarter.
Sorry, sir.
Yes.
I think the question we had was, if you do like you stop there with adding half over 4, like the way we know it's completing the square, even if you add something, you make it a perfect square. But if you try to develop what you found, you can go back to the initial equation. So some of us did that, and then we say minus 1 over 4. So that even if you go back, you can actually get the initial equation. I don't know if you get what I mean. So was it wrong to add minus 1 over 4?
Yes, I get your concern. I understand what you mean by that. So you are saying that for us not to change the meaning of this expression, we must subtract what we have added. So you wanted to write this as x squared plus x, the same as x plus a half squared minus a quarter. Well, that's okay. This makes sense to do this. X squared plus x is the same as x plus half squared minus a quarter. That's okay.
Yeah, I mean, everywhere you go and look for completing the square, I think this is what they're going to show you. So you add something, you need to subtract it so you not lose the initial equation.
Well, what my intention here was that that you make this a complete square. My intention was that you should make this a complete square. You know, this is different from when someone asks you x squared plus x is maybe equal to 6. If I ask you to complete a square on this side, then now you have an equal symbol. So what you do on this left-hand side, you must do on the right-hand side. So if you add here a quarter, you must also add it on the other side. This is different from when you're just given an expression like this and we're asked to complete the square. If you're asked to complete the square here, I need you to just make this a complete square. Write this as a complete, just there's a miss, it means there's a term which is missing for this to be a complete square. That is the term that we need to add. Completing the square is, so this is different from using the method of completing the square to find the roots of quadratic equation. In that question, I was just testing if you know how to complete the square, not if you know how to use completing the square method to find the roots of a quadratic equation. So what you're talking about here is when you're asked to use the method of completing the square to find the roots of this equation. But for this case, I just wanted you guys to make this a complete square, not to use that method to solve it. Because this is just an expression, this is not an equation. This is just a quadratic expression. There is no equal sign. So this is not an equation. It's not an equation, it's just an expression. Remember, you cannot solve an equation. I mean, you cannot solve an expression. You only solve equations.
So were you accepting both answers?
Yes, I was accepting both answers because the only part I was interested is in this. So I was ignoring this subtraction. For those who did this, I was only considering the part that you squared, I ignored the other one. Because I know you understand the method, but you are going ahead, your goal is to solve an equation that results from this. Then there was another question you were asked to use the determinant. Any more questions on that?
Maybe.
Find all the solutions to the equation by using the quadratic formula. X squared, yeah, that's all.
So the formula is x should be minus b plus or minus square root b squared minus 4ac divided by 2a. A is 1, b is 1, c is also 1. So just here we have x is minus 1 plus or minus square root 1 minus 4 divided by 2. So this is minus 1 plus or minus square root minus 3 divided by 2, which will give you negative 1 plus or minus square root of 3 times I divided by 2. Because this is a negative number, so square root of a negative number, introduce the I because I is square root of negative 1. So there are two answers here. So this is either minus 1 plus 3I divided by 2 or minus 1 minus root 3I divided by 2. These are the two solutions.
You can see.
These are the two roots for the equation, x1 and x2. They are complex roots. So some of you are doing it up to this stage and then they were saying there's no real solution. Yeah, which is okay. You actually get complex roots. So with the real part negative a half and the complex part half of 3I.
Are you awarding points at negative 1 plus or minus root 3 over 2?
Yes, I was also awarding at this point.
Okay, complete marks or just
1 mark.
Okay.
Yeah. And then the last question, you were asked to use the discriminant. So something like x minus 4x. Is it plus?
You can see there.
How about now?
Yes, thank you.
You are to use the discriminant to find the roots of x squared minus 4x plus. Is it 1
it's
or
x squared? No, it's x squared plus 4x minus 1 equals to 0.
minus 1 equal to 0.
Plus, it's x squared plus 4x, 4x, plus 4x.
You are to use the discriminant. So some of you went ahead and found solutions. I did not ask you to find solutions of this or to find the roots. You just use the discriminant and tell me how many solutions will this equation have, if it will have real solutions. So the discriminant given ax squared plus bx plus c is 0. We define the discriminant as this b squared minus 4ac. The number b squared minus 4ac is the discriminant of this equation. So in this case, just identify a, b, and c. A is 1, b is 4, c is minus 1. The discriminant will be b is 4 squared minus 4 times 1 times minus 1, which is 16 minus 4. That is 20. 20 is a positive number. So what's the conclusion? This equation will have two distinct real roots. You are supposed to find the discriminant and then make a conclusion on the sign. So some of you arrived at this but did not make any conclusion, and I was denying you a mark for that. Because if you just give me the discriminant and you don't tell me the conclusion. So those who just got 20 and did not conclude, I was denying you some mark for that. So because this is positive, the equation has two distinct real roots. The equation has two distinct real roots. Okay, so that's all you expected.
What did you?
Sir.
Yes.
I didn't understand this part 3b.
You didn't do what?
Part 3b.
Part
3. I arrive at the answer again. I just can't get it. It's part 3b.
The roots.
Problem 3b, rather. Yeah, the roots. No, not the roots from the solutions.
The one I've rubbed here, this one.
Yes.
What about it?
I got my answer. I got was x minus 1/2 plus the root of 3 over 2i.
Minus 1/2.
X, yes, x minus 1/2 plus the root of 3 over 2i.
Yeah, that's okay. That's one of the roots.
Yeah.
And then the other one is
x 1/2 minus, yeah.
Yeah, those are
Yes,
roots. It's the same thing.
Okay.
This is the same as writing minus 1 plus root 3i divided by 2. It's the same. Okay. So last time we looked
Excuse me. Sorry.
Yes.
What if you're asked to find the roots? Can you just maybe help us there? I know it wasn't asked, but
if you ask to find the roots of this.
Yeah.
So you already have a discriminant, right? The formula tells you that x is minus b plus or minus square root of b squared minus 4ac divided by 2a. Okay? Remember, it is this guy which is the discriminant. What is under the root? So we already know this guy is 20. Okay?
Yes.
Hello?
Yes, I can hear you.
X is going to be minus, what was the equation? X squared plus 4x.
Plus 4x minus 1 equals to 0.
That means b is 4. So it's going to be minus 4 plus or minus square root of 20 divided by 2. Okay?
Okay.
So this is going to be minus 4 plus 20 divided by 2, or minus 4 minus 20 divided by 2. If you like, you can simplify 20 as 4 times 5. So this becomes 2 root 5. Now You can write the first root as minus 4 plus 2 root 5 divided by 2. The second root as minus 4 minus 2 root 5 divided by 2. So that now your first root is minus 2 plus root 5, and your second root is minus 2 minus root 5. Those are the real roots.
Thank you.
Good. Now, last time we looked at systems of linear equations.
One more question.
Yes. Go ahead, please.
You haven't done problem 3D?
That is problem 3D.
Oh, there's another problem.
Yeah.
The last one?
The last one.
Yes.
What was it about?
A rectangular bedroom is 1 meter longer than it is wide. It has an area of 30 meters square. Found the dimensions of the bedroom.
So area is 30. Let the width be x. So the length will be x plus 1. You've been asked that the length is 1 meter longer than the width. The area is 30. Now you need to remember the formula of finding area of a rectangle. How do you find area of a rectangle?
Width times the length.
Width. So in this case, you should have x times x plus 1. Now that gives you x squared plus x. So remember, you're told area is 30. So that means if the width is x, the length is x plus 1. So that should mean x squared plus x is 30, which means you get x squared x minus 30 is equal to 0. That's a quadratic equation. Then use any of the methods you know to compute the roots of this equation. Okay? I want to use factorization. So I'm looking for a number whose product is minus 30 and sum is 1. Two numbers. So if I pick 6 and negative 5. Okay? 6 times minus 5 is minus 30. 6 plus minus 5 is 1. So we can write this guy as x squared plus 6x minus 5x minus 30 is 0. Then factorize, so group these two guys. So x into x plus 6 minus 5 into x plus 6 is equal to 0. Now x plus 6 is common, factor it out. We're going to get x minus 5 times x plus 6 is 0. Now remember, product of two real numbers is 0 if and only if one of them is 0. So that property will give you that either x is 5 or x is minus 6. But what was x? X was the width. Length can never be negative. So ignore this negative number and take the length as 5. And consequently, the width is 6. And it is true that 6 times 5 gives you 30. So there was one mark for getting the right quadratic equation and another mark for any method of your choice, whether you like factorization, the formula, or completing the square, and then getting the dimensions. So it's saying that the length is 5 and the width is 6. So such questions you must always conclude, because I'm not the one to decide for you whether to use X or L or W or whatever. So I'm not interested in the letters or I'm not interested in what you're using. I'm not interested in the final conclusion. What will be the length and what will be the width? Questions on this? Any questions on this? No question. Shall we proceed?
Yes, we will proceed.
Okay. So I can see we have less than 40 minutes. Let's see what we can do. Now, in the last class, we defined what's a system of linear equations, what it means to solve a linear equation, and the solution of a system of linear equations using the methods of substitution, and the method.
Excuse me, sir, the voice blurry.
It's blurry.
It's so blurry, I can't see.
Let me change my pen. Perhaps that will help. I just wrote elimination. Still blurry?
Okay. It's okay now.
Good. And substitution. And the take home that day was that all of these methods have one goal. The goal is get rid of simultaneous equations and have a linear equation, which is easy to solve. So once we have solved a linear equation in one of the variables, then you can use any of the equations that you have to find a solution for the second variable. Now, we can generalize these two methods for when we have a system of equations with more than two equations. Let me give you an example, and then I show you how these methods will help you. Suppose you are asked to solve the system x plus y plus 1, no, plus z is, let's say, 4, then y plus z is 6, then 2z is 5, maybe 2z is 8. So this is a system of equations with how many unknowns? How many unknowns do we have here?
3. 3.
Yes, x, y, and z are unknowns, and you're supposed to solve this system. So you solve this system by a method called back substitution, which is essentially substitution, but it is called back because you first of all find the solution of the last variable. So you start by finding the value for z, then y, and then x. But it's just a slight modification of the method substitution. That's why I said, once you master the two methods, substitution and elimination, then you should be able to solve any system of linear equations with any number of unknown variables. So for example, in this case, this is equation 1, equation 2, equation 3. You are all aware that a root of this will be a set of values for x, y, and z, such that all the three equations are satisfied. So first of all, it's very easy to solve for z in that equation because we just have a linear equation in z, okay, from equation 3. So from equation 3, z is going to be 4. It's a linear equation, so I just divide both sides by 2 and get z is 4, okay? That's from one of the equations. Now, I know what z is. In the second equation, there are only two unknowns, y and z. But I already know z, so I can substitute for z with 4 and find y. So from the second equation, y plus, okay, z is 4, should give me 6. So that means y must be 2. By subtracting 4 from both sides, y is 2. So now we have z is 4 and y is 2. And it is true that if I put z is 4, this equation is satisfied. If I put z is 4 and y is 2, the second equation is also satisfied. Now, the first equation has 3 unknowns. We already know y and z. So we can substitute for y and z in this first equation and solve for x. So you will have x plus y. So the y was 2 plus z, which is 4, should give you 4. Then from here, x plus 6 is 4.
You can't see below that.
So should be fine now?
Yes.
Which means x must be equal to minus 2. So if you take the set, the values x, y, and z, so x minus 2, y 2, and z 4. This set will be a solution of this system if all the three equations are satisfied at the same time. So suppose I take minus 2 plus 2. Is this the correct? Yeah, okay. Minus 2 plus 2 plus 4. So if you put minus 2 plus 2 plus 4, that gives you 4. So the first equation is satisfied. Y plus z, 2 plus 4 is 6, satisfied. 2 times 4 is 8, so that's satisfied. So it is true that this is a solution of this system, or these are roots of that system, or the zeros of that system. This method we have just used is called back substitution. Back substitution. And we are calling it back substitution because you find the roots of the values of the unknowns starting with the last. So from the last going backwards to the first. That is why the name back substitution. But it is simply substitution. So you get one value, substitute in the second equation, find the second value, substitute the first two values you found in the last equation, and find the value of the third unknown. We can generalize this method to be used for solving any system of nonlinear equations with any number of unknowns. For example, if I give you a system, let's say a1x plus a2, you can see there, if I write a1 x1 all the way to an xn is b1, then a2 x1.
So we still can see at the corner.
At the corner.
Where you wrote the A's, we can see the A's.
Okay.
A.
How about now?
Yeah.
Okay.
Yeah.
Okay, so A, this should be C1, Cn, it's B2, and then all the way to maybe Q, X1 plus Qn, Xn, Bn. So this is a system with n unknowns. So the unknowns here are x1 up to xn, where n is a positive integer or n is a natural number. So this system could be having 20 unknowns, 50 unknowns, 500 unknowns, 5 billion unknowns, 5,000 unknowns. Of course, there are algorithms that can solve this. You can write this. You can write a program that solves this kind of system in Python or in MATLAB or in Octave or in Scilab or in Sage, whichever language you're familiar with, or in Singular. But the idea behind these algorithms is simply back substitution. Back substitution. So the computer will first of all reduce this system to something like this. This is what we call a triangular system. The first equation has all the unknowns. The second equation has the number of unknowns less by 1. So this one had 3, this one now has 2. You go all the way up to the last one. So what the computer will do, it will change this system. The first will just maintain A1 up to AN, XN is B1. Then the second one, I will have something maybe alpha X2 plus maybe, so alpha 2, alpha N, XN is, I don't know, maybe now instead of B, maybe some K, all the way to the last one, maybe beta N, XN is equal to, let's say, some Ga or tau, gamma. So that this is called a triangular system. Now to solve this, I'll apply the same algorithm. Solve for the last variable. So this is a linear system. This is just a linear equation in Xn. I can divide both sides by bn and then get xn. Then I go back to the second last, solve for the second one, and I keep getting back to the first one. Now the question is, how do you reduce such a system to the system? It's just through elimination. So suppose you are given a system of 3 unknowns. Let's say 2x plus 3y plus z is 6, 4x plus 2y minus 6z is 7, 2x plus 4y minus 8z is equal to 10. You're given a system of 3 unknowns, three equations with 3 unknowns, and you want to solve this by back substitution. Your first goal is to convert this system to a triangular system, a system where I can solve for one term in one equation and then use that in the next equation to find a solution, and then you lastly put it in the first equation and find all the 3 unknowns. We're going to do this by elimination. So first of all, to convert this to what you call a triangular system. A triangular system is simply a system where the first equation will have 3 unknowns, the second one will have only 2 unknowns, and the last one will have 1 unknown. It will essentially be linear in this third unknown. Then it's very easy to solve linear systems. So then I use this solution, I put it in the second equation, as I put it in the third equation. So first of all, we are going to maintain the first system, 2x plus 3y plus z is 6. Then we want to eliminate x from the second equation and the third equation. This is equation 1, equation 2, equation 3. We keep the first equation as it is, eliminate x in the second and the third equations. How do we do elimination? If you want to do elimination by addition, make sure that coefficients of the terms in the 2 equations you're dealing with are either of, if they are additive inverses, then you can add. If they're the same, then you can subtract. So here, it's easy for me to do, so because I have a coefficient here, 2x, I can either make coefficient of x in the first one, 4x or negative 4x, and then use that to eliminate 4x from the second one. So by introducing a fourth equation, which is simply negative 2 times the first equation. So take negative 2 times 2. This gives you minus 4x. Negative 2 times 3y, that is minus 6y. Negative 2 times z is minus 2z. Negative 2 times 6 is minus 12. So this is your fourth equation. I have not changed the meaning of the equation because I've multiplied all the terms on the right-hand side by the same term on the right-hand side. So the meaning of your expression does not change. What I'm saying is—
I'm moving the bird a bit to
up.
The side.
Right.
The left.
That will be your left side, because
Yes.
that one. Thank you.
Yeah. So what I'm trying to say is that these 2 equations, the first equation and the fourth equation, will have the same roots. They'll have the same solution, because to obtain this fourth equation, you multiply the first equation by the same term. So we have not changed the meaning. Now I want to use this fourth equation to eliminate x from the second equation. So that's why I was interested in making this negative 4x, so that I will just add these 2, and then the x will disappear from the second equation. So add now equation 2 to equation 4. 4x minus 4x, that's 0. 2y minus 6y, that is minus 4y. Minus 6z minus 2z, that is minus 8z, should be equal to 7 minus 12, that is minus 5. So I now have a second equation, minus 4y minus 8z is equal to minus 5. And my second equation does not have an x variable. It's been eliminated. I will do the same for this third equation. This is 2x, this is 2x. So I can subtract them directly because this is coincidence. It is just a coincidence. It never happens like this usually, but you already have 2x and 2x, so can just go ahead and subtract. So take the first equation minus the third equation. So that give you 2x minus 2x, that is 0. 3y minus 4y is minus y. Z minus minus 8, so that is plus 9. Z should give you 6 minus 10 is minus 4. So it's a coincidence that it's very easy to eliminate x in the third equation by just subtracting, because coefficient of x is the same in both equations. So we have this as minus y plus 9z is equal to minus 4. Remember, this system is the same as this. By that I mean the solutions of this system will be the same as the solutions of this system, because we have just eliminated some terms from the second and third equations. So this is your first equation. This now will be equation 5. This will be equation 6. Now our system is not yet in triangular form because we still have 2 unknowns in the last 2 equations. We need to make sure that there's only 1 unknown in the last equation. So again, now use the second equation to eliminate y from the last equation. So you're going to have the first will be maintained, 2x plus 3y plus z is 6. The second equation in this case, minus 4y minus 8z is minus 5. We maintain these 2 equations. Then now we use equation 5 to eliminate y from this. So I need to make sure that coefficients of y in equation 5 and equation 6 are either the same or additive inverses. Okay? I can do that, for example, by dividing equation 5 by negative 4. So take equation 5 divided by negative 4. Negative 4y divided by negative 4 is y. Negative 8z divided by negative 4, that will be 2z, should be equal to negative 5 divided by negative 4, that is going to be 5/4. So now we can eliminate y, because coefficient of y here is negative 1. On the other side, it is 1. How do we eliminate y? By addition, because they are additive inverses. So negative y plus y, well, that's 0. 9 plus 2z is going to give you 11z, should be minus 4 plus 5/4. What's minus 4 plus 5/4? Hello? Hello?
Hello.
The more you participate, the more you know. There's no way we're around the cadaver, and then tomorrow you get cadaver to the different parts, and then you get to know them. It's actually difficult. Especially when you go face to face. Normally before we used to do practical on the cadaver. But this time around, we try to do it online, try to improvise here and there. But yes, the more active you are, the better you are. Like this case, I don't know. I want to try
Anne,
hello, what's happening?
Anne.
Hello? Who is talking?
Someone's mic was on.
Ah, okay. Any question up to there?
Yes, I have a question.
Yes.
So can you give 2 equations?
Sorry?
Can you be given 2 equations.
Yes, you can be given two equations. For two equations, it's just the usual elimination. For two equations, it's just the usual elimination. So now that you have transformed this system into a triangular system, you can now solve it by back substitution. Solve for z, use the value of z in the second equation to solve for y. Then once you've known y and z, put them in the first equation to solve for x. And you will have the solution for this system will be the same as the solution for this system. This is actually the same algorithm that all the programming languages use for systems of linear equations. And the whole process is usually called Gaussian elimination. It's usually called Gaussian elimination. So Abdi Hakim, if I go,
We can see something Shan, Russian or something.
Gaussian.
The first letter.
G.
Or Gaussian.
I wrote this Gaussian. Gauss was a German mathematician. Gaussian elimination. It was named after Gauss, Carl Friedrich Gauss. It was a German mathematician. He's the one who first applied this method to solve systems of linear equations. So it was named after him, where you transform a system into some triangular form so that the last equation has only one unknown. And then as you go up, the number of unknowns keep increasing up to the last one. So the way to solve it is start with the last unknown, solve for it, use that value in the second equation, find your second unknown, all the way to the first one. And you keep substituting as you go back.
Excuse me, sir.
Yes.
How did you get VI? Did you minus or add?
How did I get the last one?
No, the VI, Roman VI.
This one?
Yeah. That equation, how did you get it?
This is from here. I got it by subtraction. Subtracting equation 1 from equation 3 from equation 1. Because equation 1 has coefficient of 2x. Equation 3 also has coefficient of 2x. When you want to eliminate one variable in two equations and the coefficient of that variable is same in both equations, just subtract the equation and it will disappear. So if I did 2x minus 2x, x disappears, and then minus 1 plus 9z and minus 4 is what remains.
So you did 3y minus 4y to get y. That's not right.
What was the first equation here? 2x plus 3y
Plus z.
Plus z is equals to 6.
Is equals to 6.
And then the second equation?
Four x plus 2y minus 6z equals to 7.
And then lastly, you had 2x
plus 4y minus 8z is equals to 10.
Yes. So the second equation, I use the first equation to eliminate x from this. Then in the third equation, I'm also using the first equation to eliminate x. So you notice that 2x and 2x, coefficient of x in the first equation is the same as coefficient of x in the second equation. I can easily eliminate x by subtracting. So if I take the first equation, from it I subtract the third equation. 2x minus 2x, that is 0. 3y minus 4y. 3 minus 4 is negative 1. So that's why I have here negative y. Okay?
Okay.
And then z minus 8. So 1 minus 8 is 1 plus 8, which is 9. So that's why we have here 9z. Okay?
Yeah, I get it.
Then 6 minus 10 is minus 4.
Okay.
Makes sense?
Yeah, thank you.
So how did you get the 11z?
Yes, how did I get the 11z? Cool. So we have, let's go back to what we had before. So now we have reduced this system to, so we only have two unknowns in the last two equations. But our goal is to make sure that the last equation has only one unknown. So now we must use this second equation to eliminate y from the third equation. So the goal is to make sure that the coefficient of y here, coefficient of y in the second equation should be either -1 or +1, so that I can eliminate by addition or subtraction. And I decided to make sure that coefficient of y in this equation 4 is, equation 5 is +1. So by dividing this by -4, I'll make coefficient of y positive. Remember, if you take -4y divided by -4, this should give you y. So y has a coefficient of 1, which is positive. Now what I did is -4y, so I took -4y minus 8z is equal to -5 and divided everything by -4. So -4y divided by -4.
We can see there.
Y.
Your body is no, has been cut off on that side.
How about now?
That's okay. Thank you.
So what I'm doing is dividing the whole of this equation by -4 so that I have a +1 here. So -4y divided by -4 gives me y. -8z divided by -2 gives me +2z. -5 divided by -4 gives me +5/4. Now I can eliminate y by adding these two equations. Okay. So when you add these two equations, -y plus y, that is 0. So y has disappeared. 9 plus 2 is 11z. Okay, so 9z plus 2z is 11z. And then lastly, -4 plus 5/4. What does that give you? So this should be 1¼ -4. So -3 -3¼ something like that. Let me, to be safe, let me just write 5/4 -4. This is just addition. So now you only have a system where the third equation has only one unknown z, which you can solve by dividing through by 11. Then you can put that in this second equation, solve for y, and then put it back in this third equation and solve for x. And I explained that this process of reducing a system like this to a triangular system where the number of unknowns reduced by 1 as you progress is called Gaussian elimination. And with this method, you can find solutions to systems of linear equations with any number of variables. Doesn't matter, as long as it's a finite number. It could be 2 million, 2 trillion, 5 billion, 4, 5, 6, 7, 8. This system will work for any number. Only that as the number of equations increases, it becomes cumbersome or tedious, even for the computer. It will take a lot of time. For example, for a computer to solve for you a system that has 100 equations as compared to a system that has only maybe 4 or 5 equations. As the number of equations increase, it becomes harder and harder. It takes a lot of time. Any question?
Yes, sir. If I use substitution, is it a problem?
Yes, you will. At the end of the day, you'll be using substitution because you'll solve for this instead, then substitute in the second equation, again substitute. At the end of the day, you're using substitution. What I'm trying to show you by describing this method is that to solve any system of linear equations, any system with any number of equations, it basically reduces to the method of substitution and the method of elimination. Because for us to get this system to transform to this system, we have been doing elimination consistently, eliminating x from the second and third equation, then eliminating y from the third equation. Then now to solve, we do back substitution. Solve for z, substitute in the second one, solve for y, then substitute in the first one and solve. All I'm saying is that any system of linear equations with any number You will need to master two methods, elimination and substitution. That is what you need for you to be able to solve any given system of linear equations. Because all that are built from this substitution and elimination.
Yeah. So what I meant was actually like, for example, not using elimination for this method. For example, we have three equations. I can just find x in like find x in equations, let's say in the first and the second equation, and find an equation with two terms.
For
Yes.
example, 2x plus 12y is 7. Maybe x minus 4.
Sorry, I can't see from the other board. Yeah. Yeah. Okay.
So for example, these two equations, huh?
No. With the equation that you gave with unknown variables, but you just find x there, which will give you an equation with y and z for let's say for the two first equation. You can just it will just I think it will end up to the same thing, but I just wanted to make sure that you accept that.
I'm still not understanding your method. I mean, are you describing a method for solving system of equations with two unknowns or three unknowns? You're talking
three. I'm saying three.
Okay, three unknowns, but just two equations.
Yes. No, like, how can I explain that? So we have three equations, right? You gave three equations, but yes, in the first two, I can just find x for the two first equation. It will give me an equation with y and z over, like, for example, for the first equation, it will give me.
Okay, yeah. Now I understand what you mean.
Yeah.
So your idea is to eliminate x, then eliminate y, and then remain with z in the last equation.
Oh God.
I can help. She's saying from the first equation, you write that equation in terms of x. That means x equals 2. Then you get an equation which will contain only y and z. You do the same thing for the second equation, and then you equals both equations, right?
Substitution.
Yes, that's what she was saying.
Will work. That will work.
Thank you. Thank you.
That's a nice method. So you are saying that I get what you mean. So for example, you have x plus y plus z is 6, 2x plus 4y minus z is 7, 3x plus 4y plus z is equal to maybe 9. Then you want to write from the first equation that x is 6 minus y minus z. Did I get it right? Hello?
Yes. Yes.
Then now you put this in the second and in the third one. Is that okay?
That's okay. Yeah.
Yeah, that will work. That will work. Because this way now you'll have only two unknowns, y and z. That will work. That will still work. Okay, so let's stop here for today. We will proceed next time.
Sir,
unless there's a question.
Just about the makeup assignment.
Okay, makeup assignment. So how many of you want to make up assignment?